Alrighty. Your job during this is to pray for my VPN connection so that I can show you some. I'm like tethering to my phone because the Wi-Fi won't let me get on my VPN for my work-related demos. So data science in the browser. So I'm Jana. I'm a data visualization engineer at Stitch Fix. If you haven't heard of us, we are an online personal styling company. So basically, you sign up, you fill out a style profile, we match you with a stylist who picks 5 things, sends them to you, you try them on in the comfort of your own home, and you only pay for what you want to keep. The company, it's a public company now. It's been around 7 or 8 years, I think. And it's been very data science focused from very early on. So data science is integrated very closely into almost every aspect of the business. We have our own branch of the organization. We're not embedded under engineering or under business analytics like data science is in some other organizations. So just a smattering of all the places where we use data science. I'm going to rush through some of this intro because we don't have a ton of time with 25 minutes. These slides are not up on the web yet, but I will be deploying them later. And I will tweet a link out. So at some point, if you want to come back to them, there's a really cool animated tour of our algorithms department that you can check out. So our team, as I said, we're organized in our own branch of the company. The data scientists, who are ABCD here, are organized in verticals according to parts of the business. So client acquisition, styling, which is client stylist matching, and recommendations inside our styling infrastructure. The merchandising, one of the cool things we do in merch is design new clothes by like combining the successful features of some of the styles that do the best with our clients and predicting what will be even better. That's really fun. And then we have this data platform team that I'm part of. We're about 25 on data platform now. Bunch of sub-teams. I'm on a 4-person sub-team doing front-end work. So our philosophy at Stitch Fix in the algo department, which is what we call our data science department, is that we hire full-stack data scientists. So they are responsible for productionizing their own work. This is not super common. A lot of places there's a handoff, like data scientists kind of develop things and then hand off to data engineers who implement them. But we don't work that way. Our data platform team, instead, we work on creating tools that make it easy for our data scientists who are not expert software engineers to put together and productionize their models, APIs, and even front-end applications to surface things like dashboards and whatever to their business partners. So we kind of co-develop these apps with data scientists. One of the first things I worked on when I got to Stitch Fix 2 years ago was building out a lot of reusable React components, and we're going to look at a couple of those today. Most of ours are pretty boring. They're boring and non-presentational. They're mostly for like fetching and saving data and stuff like that. They just make it really easy to get an app up and running really quickly. And we also have a wrapper around Create React App that customizes the output by installing our private dependencies, making the boilerplate something that actually makes sense for a data scientist who wants to get started building an app based on a table in our data warehouse, things like that. So long intro, right? We are going to talk about data science in the browser, and we're going to talk about dimensionality reduction components. In particular, we're going to talk about 2 algorithms, tsne and umap. This is t-stochastic neighbors embedding and uniform manifold approximation and projection. Not going to go into the math. I'm not the best person to do that, and we only have 25 minutes. But you do need to know a little bit about what dimensionality reduction is. So let's start with this table. We've got foods, emoji foods, and an average weight per item. So 1 grape is really small, a watermelon's really big. This is in grams. And average calories per item. I just Googled these for this example. We can make a scatter plot of this, right? And we think about scatter plot as showing us correlation between variables, like this weight and calories per item. But it's also showing us relationships between items in the data set, right? It's helping us see that here's our kind of fatty items area. A bunch of the fruits are right here. These are things that are pretty low in calories, but tend to be large per item. I think that one's a cantaloupe. So we also see things clustered together that share similar attributes, at least in terms of what we're looking at. If we go into 3 columns here, carbs, protein, and fat, the 3 major macronutrients, we could also make a plot of this. We'd have to do it in 3 dimensions. It'd be a little bit trickier to visually explore, because you'd really want to do it interactive, where you could change the perspective, because 3D is difficult. You can have things that are hidden, basically because we're doing 3D on a 2-dimensional screen. So what TSNE and UMAP do is they let you take data sets with many, 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 many more columns than this, up to hundreds, or as we'll see in a bit, hundreds, almost 1,000, and apply this algorithm and then be able to group them on a 2-dimensional plane, sometimes 3-dimensional too, so that you can see similar items together and have an understanding of this high-dimensional data set that you're looking at. So the canonical data set that we can take a look at for this is the Mnist hand-drawn digits data set. So this is what the actual digits look like, or a selection of them. So these are, I don't know where they got them, but somebody got them, a bunch of hand-drawn digits, 0 through 9. Each digit is an image that's 28 by 28 pixels. And so what that's going to end up being is 784 dimensions. So here's one of the images. So basically what we're doing is slicing it up 28 by 28, right? And so if we look at column 8, row 7, that would be coded in this data set as a 0 for white. And column 9, row 7 is a 1 for black. So that's how this data set works. And so this is a high-dimensional data set with 784 dimensions, because if we want to compare all of the images, we have 784 little squares here to compare from image to image. Is it 0 or 1 on this image and on that image? So when you put this image data into one of these algorithms, this is an example result. So this is the TensorFlow JavaScript implementation of TSNE on the Mnist data set. Here, since the data set is labeled, we color code by what digit it actually is. And so you see that it works pretty well. You get these pretty, with a few spots here and there, you get these clusters of the digits that are actually the same number. So now we're going to talk about componentizing this. I gave a talk a while ago called Better Living Through Components, and this is doing components in particular for computation. Now the reason for doing this, the reason there's a talk here, is because we can't just take one of these libraries and the TSNE, the TensorFlow TSNE library, or the more recent UMAP implementation in JavaScript, and just kind of dump it into an app. Because first thing, these things are extremely computationally expensive. Even with all the tools I'm going to show you, by the end of the day when I'm working on this stuff, I'm one of those people that I like to not be at my desk in my open plan office. I go hide in a cubby somewhere. But my computer gets so hot that by mid-afternoon, I'm tethered to my desk, and it doesn't even charge, because Macs stop charging when they overheat, even if they're plugged in. It'll just stay steady state, or sometimes even keep dropping charge while I'm working. It's pretty incredible. So we need to really minimize that. Not everyone even has a 15-inch MacBook Pro, right? And we need to minimize the compute time, because we don't want a user waiting forever for one of these results to actually see something. So we want it to happen before they turn 102, right? So how do we do this? So the biggest way, although this doesn't apply to the UMAP, is computing on the GPU, and in particular, even more important, doing that outside of your main application code. So doing it in a web worker. This requires doing it in an Offscreen Canvas. We'll talk about what that is. And caching. Our data doesn't actually change super often. Pretty common in a data science org. A lot of things run on nightly jobs. So if a user is using an application and they're just going back and forward within the space between 2 pages within the space of a few minutes, there's no reason to recompute. They're getting the same input data. So web workers. These are, if you're not familiar with them, this is a way to do concurrency in JavaScript, which is always single-threaded. So they are in a different bundle, separately executing from your main app. And there's no DOM in a worker. You pass messages back and forth, and these are actually copied. You don't share data between your main app and the worker. And more like frustratingly sometimes, you have to pass certain types of messages back and forth. They have to be serializable. There's a link here to the algorithm that's used. Basically, non-exhaustive list of what you can are like things that are pretty obvious, like anything primitive, dates, blobs, array buffers. What's not, and is frustratingly not, is DOM nodes. It'd be really great if you could like, pass a canvas over, render stuff into a worker, and then bring it back when it's done. Can't do that. Errors, which makes handling errors in the workers difficult because you can't pass them back to the main app to get reported out to the user or the developer. And also very frustratingly functions. Obviously in JavaScript, since we can do closures and pass functions around all over the place as first-class citizens, it can be very frustrating to not be able to like pass some kind of callback into your worker. So the basic template for using one is you just set up a function on the worker's on message. This is just an example of how most of these libraries work. It's not exact code of any particular library, but we call the result of a tsne or UMAP algorithm an embedding. So you usually just create an embedder, and I should have called that embedder, not embedding. And then you get out the coordinates of the result and pass those back. In React, I'm going to breeze through this. Applies to any other framework library pretty much to like Vue. Basically just how you integrate this with the life cycle. Creating your worker when you first mount the component and handing the data over to the worker, and then when the message comes back, you set it in state and then probably render it. So we won't go through this in detail. You can come back to it if you want. So how to bundle workers. This can be a little tricky. Webpack is the best place to do this right now. The worker loader is what I've always used because I've been using them for a while. More recently, there's a cool package that will actually just take any function and then create that template around it and make it into a worker, which is pretty cool. The only reason I've never used this is because I'm really familiar with that template already because I've been using workers for a long time. So, but maybe one day I'll try it. I did try recently, because some of our libraries are bundled with Rollup in order to get tree shaking, which was just discussed. And it seems like the Rollup plugin might be out of date for workers, because it didn't work for me. But I didn't dive into it too deeply. Offscreen Canvas. So this is the other piece of really getting the user experience of computing a big tsne in particular good. Offscreen Canvas is brand new. It is actually only right now in mainline Chrome in the last few versions. And I think you have to be in Firefox Dev Edition, and then you have to turn on a flag to get it to work in Firefox. So this is just an HTML canvas element, but it's one that's, well, you can use it in the window as well, as this little pullout says. But crucially, you can use it in a worker. The worker, again, has no DOM, so it doesn't have normal HTML canvas. You need to use this off-screen canvas. And that's how the TensorFlow tsne library does the computing of the result on the GPU in a canvas element with WebGL. Caching, again, data doesn't change super often. We do have an escape hash, like you'll see in some of the demos later, a recompute button. We did this really simply just with using this library object hash on the data to get a key that we use for putting the result in local storage. And cache is a Boolean prop on the component. So the secret here really is that every single time you compute, you try to store the result in local storage, but you just don't pull from that local storage unless the person has the cache prop turned on. So that means that if it's off, but then somehow they turn it on, if that's part of your app that you let them turn it on, then they can pull from the cache immediately without having to run it again. I'll breeze through this again. Again, just using the lifecycle to do this. Now for the developer experience, most of these are basically the same as the user. Like, you don't want your computer to burn up. It kind of does anyway when you're doing this. Like, sometimes I have multiple tabs open or something, which is terrible. And you don't want to wait forever. Caching is really big for the developer experience when you want to iterate on how you're displaying the result, right? You don't want to recompute every single time that you make a change to that code. And then the componentization is really the biggest part of the developer experience. Taking this whole procedural kind of flow of doing a computation, storing the result so you can cache it, and making all of that declarative in a component form makes it extremely easy to reuse in a bunch of different contexts. Yep, I already covered that. So now we are getting into the demos, which should be fun. So the first one here, I have in the code behind here, the caching turned on. So we're going to see the Mnist hand-drawn digits. And it should load pretty fast. There we go. Pretty darn fast. So this is the tsne. Tsne always kind of tends to create this like amorphous circular type shape. UMAP really doesn't. So we'll see the difference there in a minute. So the UMAP, I'm going to get started because it will take a while. And this initial step is not very fun because this is actually, it's doing some like initial bootstrapping. And so you don't actually see even the iterations, which you will see. So that's another thing that's a prop on the component, is saying whether or not you want to see, these are iterative algorithms, so if you want to see it while it's converging, or you can just wait till it's done. So we will see it while it's converging. And the reason I put that little hedgehog in the corner is to prove to you that this is happening in a web worker. If this was not in a web worker, that GIF would be frozen right now because the compute we're doing is really a lot. We're using up a ton of resources. Also, as the iterations get going, they'd be super, super janky and slow. There might still be a little bit of jank, especially since I'm presenting. So like my GPU is doing more than usual. But oh, that looks pretty good, actually. So yeah, the UMAP in general takes fewer iterations to converge once it gets going. And it doesn't create that circular shape as much, so that's it. One of the really cool things I think in this example, and I think UMAP does this a little bit better than tsne, is it even sees sort of neighborhood approximations and clusters them appropriately. So this chunk right here, the dark blue is 7s, the dark brown is 9s, and the purple is 4s. And so you can actually, if you think about it, you can see how all of those might be close to each other, because they sometimes can look a little bit like each other. And like the ones that are the most isolated are, like that's 0. This one is 6s. Again, and those two are close to each other. You can kind of see why that might be true. So it's pretty cool. You can see some interesting things out of UMAP. And so now I will show you some interesting things in the kind of data that we work with at Stitch Fix. Let me get out of full screen. So this is where my VPN connection is fun. Yeah, I'm just going to do that. All right, so this is actually a UMAP on items of clothing. So, and this particular, what we're using for the dimensions here is a model that is still under development, actually, by one of our data scientists, using computer vision to predict features of clothing. So things like sleeve length, collar type, anything and everything you can imagine. There's a lot of dimensions to this. So using the actual, what we want to, the goal is to be able to take an image of a piece of clothing and then find other things that are similar to it, either in our inventory or elsewhere in other like data of images of clothing. So this is a run of UMAP on a particular, I found developing these demos that narrowing it to a particular color is helpful, although I think this color is bad. So let us go. It's too dark on the screen here. Let us take that out and this is one of our fetch components. And we'll put pink in. I think that might show up better. Oh, please get the data. also have been running into limits on header size, which is why I just checked the console. Oh, OK. Next, we're fetching from many services here, basically to get all the attributes from this model, and then also get the image of the item, et cetera. Oh no, blank screen. Oh, it's just taking forever to load the images. OK. Well, we'll stick with light pink then. We can do another version of this, but I will keep the color the same, because it's taking, I should have predicted this, that it would take a while to load all the images on my poor phone connection. So they're just popping. So we're not seeing the iterations, because they happened before the image is loaded. But you can already see, actually, this kind of makes it fun to see how things build up. So here's like some flowy short sleeve things. I need to look at my screen. We have like button-down shirts over here. Let's see, long sleeve, cold shoulder. Not a lot of pants yet. I guess there are not a lot of light pink pants. Yeah. So another one thing you're noticing here that makes it a little difficult to assess this is with images rather than little tiny numerals with the Mnist data. We have a lot of overlap, and so that's a little hard to deal with. So the newest thing that I've been working on is a linear optimization, an alignment algorithm that takes the output of the dimensionality reduction and then kind of blows out the clusters and figures out the optimal place to preserve neighborhood relationships but have everything on a grid. So I think we've got, well, they're still loading, but let's try to look at that grid. Waiting for the create React app to rebundle. I think the timing of the talks here ended up being rather good. I think it was so busy doing other things it just didn't recognize. Hopefully it's doing the alignment code now. We'll see. All right, the alignment is not fun to see the iterations anyway. So while this is loading, I have one more demo that's in the deck. And the images are on my computer, so they don't have to load. So this final demo, fun one to land on, is all with this guy's stuff. So Bob Ross, the famous painting instructor, a long time ago, or at least, I don't know what your definition of long is, but I think maybe 5 years ago, 538, hand-coded a bajillion attributes of every Bob Ross painting from every episode. And the data is on GitHub. So I took that data and I made it into a little UMap. So that's, yeah, you get, I think all the oval ones ended up over here. Again, this is tough. So this one will give us the grid. So this is fun to zoom in on. It looks like we're in a mountain section here. Lots of Bob Ross paintings with mountains. Now we're in streams, foliage, more mountains. Yeah, some mountains. There's usually there's got to be a water section somewhere. Yeah, here's like the ocean paintings. Well, that's the grid, and this is here now. So here's a grid of those light pink clothes. So there we do see like pants clustering, things like that. And polo shirts here. This alignment to grid isn't perfect. It tends to kind of spread out clusters on diagonals, so it kind of takes a little practice finding the relationships, but it's fun and a work in progress. So, and then finally, we are going to open source this. So look for it sometime soon. I'm sure I'll tweet about it. We're going to call it React Flatland, just these wrapper components. Obviously, relying on great open source libraries that already exist for these dimensionality reduction algorithms. So thanks.
So the first thing, so I saw something come on Twitter. Someone said, it's super cool that your talk on data science in the browser is also a secret introduction to working with web workers as well. Did you know that going into your project, or was it kind of a discovery?
Yeah, I've been kind of a data visualization specialist for a while. Previously at a startup, not at Stitch Fix, is where I first started using web workers. In that case, it was just because we were working with a ton of data and we needed really, really fast filtering. So a pattern I use a lot is to have a worker basically cache, if you have a huge amount of data that you're visualizing in an app, have a worker that just kind of caches it, and then you pass, every time like a user changes a filter and you need a different subset of that data, you pass the message of like, give me this subset, and then the worker does the filtering and passes it back, and that makes it, tends to make, even with, I don't know how many data viz people there are, we're still using like something really fast like cross filter in the worker, but it's still, we're talking about maybe 1 million data points, so it just makes it a lot faster.
Would you say that data science, no matter like if it's web or other I guess ways to do it, I'm not a data science person, but would you say that there is always some form of performance in terms of either hardware or in the browser that you have to be aware of?
Yeah, definitely. Even our data scientists, when they're, most of the time they work in Python, sometimes R to a lesser extent, and they even struggle with, they're dealing with very different timescales. Like, it's okay for a job to take 3 hours. It's not okay for a job to take a week. Like, I was working on a project where the job would literally take a week to finish, and by that time the data that was the input was like a little bit stale. So, working to figure out how to make things perform faster is definitely a big part of the job.
Mm-hmm. In terms of performance, what is usually the first thing that you'll usually take a look at?
Oh boy. I mean, with database stuff, it's always like, how are you rendering? So all the things I just showed are in Canvas, even rendering the images in Canvas. I use SVG a lot when I can because it's easier to make tooltips and things like that, but SVG gets into performance pitfalls pretty early. So yeah, rendering is usually the first thing I look at. Okay.
So if you could make changes to the web platform to better support data science in the browser, what would some of those changes be?
Ooh. I mean, some of the stuff that's going to be coming with like WebAssembly is probably what would be on my wish list, but making that easier. I think we were maybe joking about trying to put something in WebAssembly that we were doing, and then I Googled it, and I was like, whoa, no, I'm not. This is going to take too much time. Mm-hmm. Better concurrency in JavaScript, too. I think there is. I was just reading up on the worker page, and I think there is something coming where you might be able to share data, like pass by reference, basically. So that might be interesting.
Mm-hmm. Have you used web workers to solve other problems?
Not really. It's usually the only problem I've ever solved with a web worker is a huge data set that I need to do something with. I guess once in another app, I basically just did the pattern of having the worker store a huge cache of data in order to not keep reloading it. So it wasn't for the same reason. It was more like because of the way the app grew, it was a little tedious to like redo and it's a large amount of data. And so in that case, just to get it from our data warehouse, like that time took a long time. Mm-hmm. So yeah.
So also, what are some of the challenges of working with React for doing cool stuff like this?
Oh, I don't know. I've actually, the startup I was at before, we were extremely early adopters of React in December of 2013 when it launched in May of 2013. So I'm a little bit of like a React fan, like super fan. So I don't know. I don't think I have any complaints. I love hooks. I didn't show any of the new hook stuff because this library predates hooks, but we're someday there will be a hook implementation of computing these things, for those of you who know about React's new hooks.
All right, let's just check Twitter one more time. But while I do that, it sounds like, at least with data viz, like a lot of it, especially on the web, you have your data science background, but you also have, this experience kind of with like web performance and web development. How do you kind of manage that? This is all like kind of this bundle at the same time, and you kind of just, adopt, new things and things like that. You want to explain that process?
Yeah, I think so. Or if I understand the question correctly. So I don't actually have a data science background myself. I have like more than some people because my PhD, we actually did a lot of quantitative work. But mostly I rely on working with data scientists. And in terms of how we choose how to put things together, almost all the stuff we work on, especially on my team, like the apps that we build are internal. We build pretty fast and loose. We pick our tools. And everyone in the department, data scientists included, also have a very large amount of autonomy. That's a company value and department value. So it's mostly just kind of trying new things, and then when it doesn't work, not doing it again.
Gotcha. Well, thank you so much.
Thanks.
Okay, one more round of applause.